Let's wait for a couple of minutes and then we will start. And we will continue with ray object intersections. We are going to finish it today. And we may, if we have time, we may even start talking about how we can compute the color of a point on a surface of an object by with a simple model of interaction of light sources with that surface point. Okay, so that's the second set of slides, ray tracing shading. Okay, so where are they? Here. So shading is the term that is used to indicate that colors have it's the variation of a color along the surface. In Turkish, it's not gölge, it's actually tarama. I mean, caricaturists, they when they do tarama, they actually are doing shading. Or you may also say gölgelendirme or tarama in Turkish. It means shading, and it's different than shadow. Okay, shadows are shading are two different terms, and shading actually a surface point which is not in shadow is still shaded in different intensity of the color the material is in. Okay, so it allows us to give the three-dimensional feeling of a scene to those objects. For example, right now you're seeing my face from the camera, and the one part of my face is brighter than the other part of my face, which means that it's not actually in, I mean, it may be in, I mean, shadow and shading, I mean, actually both of them are in shadow actually, in the sense that my face cannot see the sun directly. Okay, the sun rays do not come to my face, I mean, directly. But there is ambient light that is bouncing off the walls around here. And the coming light from this direction is actually larger than the light that is bouncing off the wall, and therefore it's shaded in different intensity. Okay, so we are going to talk about shading after the geometry slides are finished. Okay, so let's start. If you remember, we talked about how we generate rays originating from an eye point and passing through a center of a pixel. And based on the resolution of your image, you're going to be generating a certain number of pixels. And you will be computing the color of the entire pixel based on this ray, based on this single ray. Sometimes there are some different versions of ray tracing in which instead of shooting a single ray to a pixel, a random sample of rays can be shot at in a pixel's area. And the colors that are computed for each of those rays could be averaged for that pixel. This will allow you to have more like a higher resolution looking image if your actual resolution is low. Okay, especially, I mean, when you already have a high resolution image like 1000 by 1000 and you're viewing it from far away, you will not notice the differences between pixels. But if you zoom in, you're going to see, especially at the boundaries of the objects, you will have some zigzags because the center pixel, since we are shooting a single ray at the center of the pixel, that ray may not hit an object, but maybe part of the pixel is occupied by the object. If that part is not passing through the center, we will just treat the whole pixel as a background pixel, although part of the object is actually passing through the pixel. This will happen especially when the resolution is very small. I mean, you have very large pixels. You will see this zigzagging effect, and the shooting random sample of rays to a pixel in different positions is one thing that you can do to avoid that zigzagging. But another thing you can do to avoid is just increase the resolution. If you increase the resolution, you will see those effects much little. All right, so we have talked about how we get this ray equation, and at the end we get ourselves a ray equation. RT is equal to E times dt. D here is the direction from the I point. It's the vector from this E to S, or in other words, S minus E gives me this D vector, the direction vector. And this is a parametric line equation. And after we have our ray as a parametric line, we can do all kinds of intersection tests with it, with the objects in the entire scene. So what we will do is, in the most basic version of ray tracing, the objects in the scene are treated one by one. They are not. There is no data structure that organizes the objects in my scene in a hierarchical manner, and therefore even those tiny triangles that comprise an object, we have to go over those tiny triangles one by one. If your scene contains 100,000 triangles, you have this ray triangle intersection for all of those 100,000 triangles. If you have 10,000 spheres, you go over those spheres one by one. That's the most basic version, and actually nobody uses that basic version practically, because you could easily implement a data structure which organizes the scene in such a way that these intersection tests that are unnecessary. For example, you have 100,000 triangles, right? Imagine you put a bounding box around those. 50,000 of them are maybe part of one object, 50,000 of them are maybe for another object. These 100,000 triangles may be in different places. And if you have a single bounding box with just 6 sides, all right, a bounding box, a rectangular bounding box, is just 12 triangles. I mean, if you just restrict yourself to triangles and spheres only, a rectangular box which has 6 sides, every side could be represented by 2 triangles. Therefore, with 12 triangles, you can represent the whole bounding box. It's just 12 triangles compared to 50,000 small triangles that are in it. Imagine your ray does not intersect this whole box at all. What does this tell you? It tells you that you don't need to do intersection tests with none of those small triangles that are inside the box. So with instead of doing 50,000 intersection tests, with just 12 intersection tests, you avoided 50,000 of them. I mean, if the ray doesn't intersect. If your ray intersects the box, you have to go inside. You have to figure out which of those smaller triangles that are inside the box. And one idea could be, okay, inside the large box, maybe I can have 4 smaller or 8 smaller boxes. Okay, so you can actually subdivide your space into smaller and smaller regions, starting with the largest ones, and you can have a hierarchical organization of your data. And there are data structures like these, like octrees. Octree, let me write in the chat box. In 3 dimensions, there are octrees. In 2 dimensions, there are quad trees, meaning that octree, it's a tree in which the branching factor is 8, hence the name octa. Basically, when we have 3-dimensional space, each primary plane, for example, xz plane, xy plane, or the yz plane, each of them divides the plane into 2 half spaces. If you use all 3 of them at every level, I mean, if you use 3 of them to divide the space into 8 regions at every level of the tree, you get a tree with a branching factor of 8, hence the name octree. And another organizational structure is bounding volume hierarchy. It's not as regular as an octree. Let me also write that in the chat box. Bounding volume hierarchy, or BVH. Okay, the acronym BVH. If you see this BVH, it's also it means that it's a data structure that is used to organize the objects in your scene. Okay, so we're not going to go into implementation details, or you're not going to describe them in detail. in this course, but we will just mention them when we talk about how the ways to speed up ray tracing and basic ray tracing algorithm. Okay, so let's go over. By the way, let me also, before we start the object intersection test, last time, if you remember, I was trying to, we were looking at a scene with 3 spheres in it, and I was trying to change the up vector. So we were, instead of looking the spheres directly, I was trying to look at an inclined manner. But the way the up vector, I was trying to change the up vector to do that. But actually, I should have changed my gaze. Because even if the up vector is like this or up vector is like that, it doesn't matter. Actually, it's automatically corrected to be orthogonal by the code that I have written. Here, given if any 2 vectors, okay, given any 2 vectors, they define a plane. Okay, so the gaze actually is fixed in our ray tracing input. So whatever the gaze actually determines where we are looking at. Okay, so the gaze determines the center of the image plane that you're looking at. So this is your gaze. Now, as you can see, without changing the gaze at all, I can have this another degree of freedom. Okay, without changing the gaze vector, this up vector could be tilted left and right. So that gives me another degree of freedom which I want to fix. And therefore, if you look at from the side, this gaze vector in the input, I gave it in a flexible manner. I don't need to give it as 90 degrees. Even if I give it like this or I give it like that, for example, if I give it like this, it will be automatically corrected by the code that I have written to be orthogonal later. So what does this gaze vector, up vector do then? It actually defines the plane, the YZ plane. The z-axis is the gaze vector. The up vector here is not the actual, for example, the actual y-axis may be this one. And if I give the up vector to be this in the input file, as you can see, they're still on the same plane. This the input that I give in the scene file, in the camera file, actually is just used to determine this YZ plane. Because after that, after you have the YZ plane, you first find the x-axis that is coming out of this, and by using the x-axis vector and the gaze direction, you again do a cross product to find the actual vector that is 90 degrees to both of them. Okay, so that was the reason we were not able to. I mean, if in the input you change the up vector just with, in the same plane to be this or that, it will not change the way you look at the scene. All right, it will still be always be corrected to be like this. So what I need to do was actually to update the gaze vector. If you want to look at the scene as if you're looking from an upwards direction, you can change the eye vector up. The eye position, you can put it up, and you can then tilt your gaze vector down so that you are looking at those 3 spheres from a higher angle and looking down. All right, so that's actually that correction I have done is simply in the code. If you look at the simple ray tracer version 1, no, simple ray tracer. So if we, it was I think in read scene, yeah. When we are reading the scene file, we are reading the read camera. Yeah, when we are reading a camera file, as you can see, we are first reading the eye position. The first 3 values in the camera file are the position of the E focal point, eye. The next 3, the following 3 floating point values are the gaze vector where we are looking at, and this is the up vector, which is, as I said, not necessarily given orthogonal to gaze. I give this as a flexibility for the user because sometimes you may not directly, you may want to change gaze in the input, but it may be difficult to compute manually an orthogonal vector that is vector that is orthogonal to this. So this one, just I always give 0, 1, 0 to this one, okay, to indicate that it's not tilted left and right. If you just give, even if you change gaze down or up, if for this up vector, if you just give if for this up vector, if you just give 0, 1, 0, it means that it's not tilted left and right. The YZ plane is always, I mean, it's going to be up in the real world. Your horizontal pixels are going to be parallel to the x-axis. This is what it means. As you can see, what we do is we first find the x-axis of the camera by cross-producting gaze and this v vector. You can cross-product these two vectors. They don't need to necessarily be 90-degree orthogonal to each other at this point. Okay, at this point, cam v and cam gaze are not orthogonal to each other, but they define the plane. Therefore, by using their cross product, I find the x-axis vector, the u direction, and I normalize the u direction so that it's a normal vector. And as you can see, after that, I recompute, I update the up direction by cross producting the x-axis with the gaze. So this is the place where it is corrected. The input v, which was not actually orthogonal in the first place, is corrected now to be orthogonal to both u and the gaze. I normalize it. The gaze is also normalized. Now at this point, I have my three vectors that define the I position and its coordinates x's are defined. All right. So, any questions about this? By the way, in the assignment, you will not need to do such a thing. In the assignment, we will always give in the input file v as orthogonal to gaze. Okay, and the assignment will be announced, I think, on Friday this week, on 30th of October. In 4 days, you will have the assignment, which will be implementation of this ray tracing algorithm. But the input file format is different than what I'm using here. I'm using something very simple just to show you how ray tracing works, but you will have to implement something entirely different. I mean, the main ray tracing algorithm will be similar, but the input file, for example, is going to be probably different. All right, so let's continue with the geometry, ray tracing geometry. So we already talked about the ray sphere intersection, right? So here, in order to intersect our ray with the objects in the scene, we will do intersection tests with our ray with the objects. And the two primitive objects that we will learn how to intersect are spheres and triangles. So a sphere, for the sphere, we are going to use the implicit sphere equation and just plug in our ray equation inside it, and it will give you a single quadratic equation with only one unknown, t, and we solve for t. And here is actually, we already known about parametric lines. By the way, you had your recitation last Friday, if I know correctly. Bilgin gave the recitation. I hope it was useful. So I'm going to skip this parametric lines format slide because we already talked about it when we were forming our ray equation from the eye point to the center of the pixel. Okay, so as a reminder, in rays, and as we have a parametric line, this d vector actually defines two things. The first is the direction of the line. Another thing, which is the magnitude of this d, defines the unit of t along the line. Okay, this is very important. So we can actually, in this d direction, we could have we could have scaled this d vector with 2, for example. Will it be a different, let me ask you a question. Will it be a different ray if the equation is RT is equal to O plus T 2D? If I just multiply this d with 2, is it going to be a different line in different direction? The answer is no. It will still be the same line. What happened when I multiplied with 2 is that I changed the units of t. So this basically the length of d defines what is your one unit. I mean, if you say 2d here, which means that d is twice like this. For when t is equal to 1, then you will be at this point in that case. Okay, so you change your definition of one unit with the magnitude of d. So this is really critical, because sometimes you always think that this is critical in such sense that, for example, if you normalize this s minus e vector, look at this d vector here. If you also try to say that, okay, I want to have my ray equation, but I want to normalize the direction vector. If you normalize it, you may be in trouble in terms of determining whether an object is in front of the image plane or not. If you leave it unnormalized with s minus e, it means that the whole initial ray, which starts at e, and when as it passes through the center of the pixel, at that point t is equal to 1. So this is one unit of this distance in your ray equation, and this is really easy. Maintaining it unnormalized like this as s minus t is really convenient, because you don't need to think about the direction of, because the distance of from e to s, as you can see, is changing as the angle that we make. For different pixels, the length of this ray is different, right? It's the shortest vector is this one from e to m, and all the others are longer than this m minus e vector. And you have to keep track of their actual distance values if you want to try to determine whether an object is in front of the image plane or not. But if you keep it unnormalized as s minus e, you don't need to worry about that. For you, that t parameter will always be between 0 and 1 from e to s. Whether s is this, whether s is this, here again, t is going to be 1 here. T is going to be 1 here for these different rays. That parameterization, t, is going to have different units based on how you define it. Okay, so this is therefore this parameter t is really important. How you need to keep track of what it means, and also you need to understand what larger than 1 means. Okay, here's a question for you at this point. Imagine I have my ray intersects. Let me actually draw it on GIMP in my question. Yeah. If all the vectors are normalized, the image plane, it may be, if you all vector, it's not going to be a sphere actually. If it actually, it's like your question is so there's a question saying that asking that if all the vectors are normalized, then the image plane will be a sector of a sphere, right? So actually, if all the vectors are already normalized, okay, if their length are all 1, if you generate those I vectors, the pixel rays, if you generate those pixel rays, and they happen to be all normal vectors, then it means that your image plane is actually a sector of a sphere. Exactly. But doesn't mean that you still may have an image plane which is rectangular. And if you normalize those vectors yourself, it will not be, your image plane is not affected by that. Your image plane is still rectangular, straight, doing like that. You just normalize them, and by normalizing, you lost the information that you hit the image plane at t is larger than 1. Okay, so you just change the unit. Normalizing means changing the unit along the vector. Okay, so you can explicitly normalize it yourself. But what I get from your question is that if they already happen to be normal vectors, normalized vectors, you generate these and you see that all of them are already normal vectors. Okay, then yeah, you're right. It has to be, if they're all same distance, it must be you're looking at an image plane which is spherical. Now, I hope that answers your question. Oh, the view distance. That's in games. There are really few games that actually use ray tracing. In games we are using a different algorithm. We don't generate these raised array equations. We are going to see that forward rendering pipeline that is used in games in the second half of the course. But the distance option, view distance, is actually indicate the distance of the image plane, the point M. In games, this point M actually is indicated as that parameter. Let me go back. Okay, so the distance between the distance of the vector M minus E is the view distance that you specify. Sometimes it's called the distance to the near plane, because the other algorithm that we are going to see in the second half of the course will actually be using like a cutout pyramid shape that extends here, and it has a near plane and a far plane, and this is the view distance is the distance of the near plane to the eye vector. Yeah, it's not, as I said, it's not constant for every pixel to the eye point, to the eye position. Yeah. When you're setting up a parameter, it's just like this distance. We give this distance as the parameter also in ray tracing. We don't specify all of the distances of the rays. We just say the distance of the image plane, the distance of the plane to the eye point is given as the view distance. Okay, pixels distances may differ as you stated. Now, let me ask you a question. Let me get a new. Okay, imagine I have an image plane that is here, and I shot a ray. This is my eye point E. I shot a ray from this pixel, and it hit an object that is here. Okay, so, and it hit this point. I'm going to be seeing this point. Now, there is a light source right here. Okay. Now, let's call this P, point P. Let's call this point L. Okay, these are points. A point light source here, a point here. Now, I want to determine whether P is in shadow or not. What should I do? There's a single light source here. Forget about reflection from other objects. Just what's shadow? When does, for example, this P point P is in shadow? You can write your answers in the chat box. Exactly. So everybody, yeah, actually, what we need to do is we shouldn't actually bouncing the ray is something else. When you bounce the ray, it may go this direction and see whether it sees another object. Okay, so bouncing is you'll use it for reflections, but here we don't need to actually do ray bouncing. Actually, it's again rays bounced. Okay, you may also be right in the case that we bounced the ray, but actually we don't bounce the ray as if the light is hitting the surface and reflecting in the same direction. We actually form this vector directly, right? This is the, I mean, if you look at this point P, the light ray that is coming to this point P is this ray that I have just drawn, right? I mean, we don't need this normal vector at P at this point. Why do we need the normal vector? I mean, it may be looking this direction. I mean, you need the normal vector if you're going to bounce the light. For reflections, you will need that. But look at this. I mean, if you know the position of L, if you know the position of V, it's this ray that is hitting because this is in every direction. So it's actually, we will form this ray regardless of the normal. Okay. Light magnitude is again, to compute the light magnitude, we will need the normal vectors, but I'm asking, the question that I'm asking is not the magnitude of the light ray that is bouncing off from here. My question was just a very much simpler than that. Is this point in shadow? Okay, in order to figure out whether it's in shadow or not, all I need to do is form this vector L minus P. Okay, L minus P actually is going to be the vector in this direction, not this one. Okay, L minus P vector. You could have formed P minus L. It doesn't matter actually. What matters? I mean, if you put P minus L, L minus P, it doesn't matter. Okay, these are two the same vectors in different directions. But let me, what I'm going to do is this. Look at this line equation. Let me use a variable. Let's call it A, okay, or S. Because it's like a shadow ray. Let's call it ST is equal to P plus L minus PT. All right, exactly. So Bugra, this is exactly what the answer that I was looking. I mean, yeah, that was the exact answer I was looking for. I mean, if the shadow will not have gradients here. Our shadow is something binary. The gradient that you're talking about actually is about shading. All right. So when we talk about shadow, if we have a single light source in the scene, a point is either in shadow or not. All right. Shadow is something binary, unlike shading. The shading, I mean, we have, for example, you may ask that how can it be binary? Because the boundaries of shadows are not sharp. We have like soft shadows in real life. Okay, we have soft shadows in real life because our light sources in real life are not really point light sources. If you have a mathematically point light source, it will mean that the shadows will be very sharp. So let me repeat that again. Shadow is something binary. So a point is either in shadow or not. Okay. The shading of this point, on the other hand, is something else. When it's not in shadow, the color of the light that is reflected off the surface will be different based on the normal vector, based on this light vector. It will be different. So there is no atmosphere. Our simple ray tracing environment is really simple. We have lots of abstractions. Here we have just a single point. We may have multiple light sources, but it's a point light source. Light rays are really sharp. They do not diffuse in an atmosphere. Exactly. So a point is either that's another good point. Another question: is it going to be pitch black when it's in total shadow? No, we are going to have the light. I mean, the intensity of a point here will be composed of three components: ambient light, diffuse light, and specular light. Okay, we will have a simple shading model which will be compute the light or the intensity. Let's call it intensity. The intensity of a point will be composed of these three components. This is also, I mean, this is a model that people have come up in real life. This is not how it happens. I mean, light rays accumulate actually, but probably these are not three separate components like this in real life. This is just to introduce these different effects that we see visually. This is a simple model. It's a very simple shading model which is composed of three components: ambient, diffuse, and specular. It will not be pitch black. So when a light ray is in, when a point is in shadow, what will happen is that it will not have these two components due to this light source. It will only have this component. And if it's non-zero, it means that if it's like the default intensity of all the objects, even in the absence of light. Okay, in the absence of light, what is the default ambient color? I mean, it's like this ambient is like light rays that are apparent everywhere, but not due to this light source. That's the starting lighting, or that's the default lighting you would have even in the case of total dark. Okay, that's what we call an ambient color, ambient light. So this ambient component, based on how large it is, it may be black or not. Okay, but I mean, the reason that I just asked this question to show you that T parameter, and Bugra gave the correct answer here. When you form the equation like this, remember for the other intersection, we were only interested in this intersections of the objects in which t is greater than 1, right? Here, because at this point, before the image plane, t was between 0 and 1. And t is greater than 1 for this pixel ray. We were interested in intersections in which t is greater than 1. But if an intersection is here its t is greater than 1, does it cause a shadow? No, actually, it's if you form the equation like this, L minus P, you're only an object. If there's an object only in between this and P and L, it may cause shadow. All right. So in that case, we will be interested in intersections which are between 0 and 1. Another thing is, I mean, for example, you should avoid intersecting the ray itself with the object itself. You need to be careful about that. Otherwise, even if you don't have, I mean, when you have, if you have the object itself, the object intersects this ray at t is equal to 0, so you cannot have equality. Even if you do not have equality and you have strictly larger than 0, because of floating point errors, self-intersections will cause small patches, I mean, like a noisy speckles of shadow. Therefore, we may actually, instead of using 0 here, we can use an epsilon value to indicate whether it's in shadow or not. Okay, so yeah, I mean, the purpose of this question, we will come to shadows later. The purpose of this question was for you to understand this parameter t is really important. Sometimes we may want it to be between 0 and 1 to figure out whether there's a shadow or not. But if in order to determine whether our pixel ray sees an object or not, we want t greater than 1. All right, I hope it's clear. But yeah, those are all very nice questions and answers. All right, so let's we did the intersection with spheres. I'm going to show you this ray plane intersection. I'm going to show that ray plane intersection to you next. The ray sphere intersection is the implicit sphere equation, in which it defines the points on the xyz is a point on the surface of the sphere. As you can see, this is the squared distance. This part of the equation is actually directly the Euclidean distance, the squared Euclidean distance of xyz to the center of the sphere. It's equal to the squared distance, which is the radius of the sphere. Okay, so if we just plug in, if we have a parametric ray equation, if we plug in its x, y, and z components separately, here we will only have one unknown parameter t in this quadratic equation, and we solve that and we find a ray where our ray hits the sphere. And since this is a quadratic equation, there are three possibilities. Either there are no real roots. In that case, our ray is just not intersecting the sphere. It may intersect the sphere in 2 points, or it may be tangent to the sphere at 1 point. In that case, we may also consider that as an intersection. Now, let's before I finish today, I want to talk about ray triangle intersection. You don't need to memorize these formulas for ray triangle intersection. There are two methods, but one method that I use is this, which is easy to describe, but more inefficient in terms of complex. I mean, all of them are O1. They require constant number of operations. But you are going to see in computer graphics, okay, I hit the wrong thing. In computer graphics, asymptotic complexity is rarely the concern here, rarely in discussion. Actually, instead of asymptotic complexity, in computer graphics, we are interested in making very small optimizations to what we are doing. For example, avoiding floating point operations is really important. I mean, although asymptotically both of them may be ON, but if one does just integer arithmetic, the other floating point arithmetic, the integer one may be faster. But these days, with the floating point operations much efficiently implemented on CPUs, the distinction is becoming less clear, but we are going to come to that. But here, in terms of complexity, they are both O1. I mean, intersecting a ray with an object, with a single object, is O1 time for our spheres, for our triangles. Now, I'm going to show if we have a ray like this, how can I intersect it with a triangle whose vertices that I know as three. So this is a three-dimensional triangle, and I want to know whether this intersection point P, I mean whether my ray intersects. So for another triangle, there may be no intersection, D, E, and F. And this is my ray T. Okay, so the first method that I describe is going to be the simple to describe, but more inefficient because it involves lots of cross products. It's like this. First, I find out the point where my ray intersects the plane of the triangle. So when I have a triangle, the triangle defines a plane, a three-dimensional plane. First, I find that intersection point. For example, it will even intersect the plane of this triangle. It may be somewhere here. If the plane, let's call it P2. Okay, so the triangle, this ray may hit the plane of this other triangle, this one, triangle 2, at P2. Anyway, so the method is like this. First, I form this plane equation. I intersect the ray with the plane. After I do ray plane intersection, I find the intersecting point. I find out that whether that point P is inside the triangle or not on that plane. So here P2 is outside the triangle, P is inside the triangle, so there's intersections. Okay, so in order to figure out whether a point is inside or outside the triangle, I use this cross product rule with three cross products. I form these edge vectors in counterclockwise direction. If you look at these edge vectors in counterclockwise direction, this point P is to their left if it's inside. If it's to the left of all these 3 points, all these 3 vectors, edge vectors, then point P is going to be inside. Otherwise, for example, for this one, it's to the right. Okay, so it's outside. For this one, for example, it's to the left. It may be inside for this, but for this one, it's to the right. So how do you determine whether a point is to the left or right? By cross products. Okay, so I form this vector, for example, P minus A, B minus A. If I do B minus A cross product, P minus A, if the magnitude of the Z value of this is greater than 0, it means that P is inside the triangle, to the left of this. Because when you do this cross product, if you do the angle like this, B minus A cross product P minus A should have a Z value of magnitude greater than 0 if P is to the left. If at any one of those vector computations, so I will do the same thing for C minus B, P minus B. So C minus B cross product P minus B, and I will also take a look at A minus C cross product P minus C. I will look at these things, these 3 cross product. If in all of them their Z component is greater than 0, it means that the point P is inside and I have found an intersection. Okay, so how do we generate the plane equation from these 3 points and intersect our ray with the plane? It's very easy actually, like this. The plane equation, since I have these 2 vectors, B minus A and C minus B, if you cross product B minus A with C minus B, sorry, this is going to be cross product. Take any of those edge vectors. Okay, if you cross product them, it will give you the normal vector. So it will give you a vector which is orthogonal So since both of them are on the same plane, look at this b minus a and c minus b. If you actually, but at this point we don't know p, okay? We don't know the intersection point. So this inside-outside test is the second step of the algorithm after you find p, okay? Now I'm describing the first step of the algorithm to find this intersection point p. Right now we don't have p. Therefore, you can only use these vectors that are on the same plane. If you cross product this, the result will be some vector ABC. Oh, by the way, I talked about the z component of them directly. Actually, you should have corrected me. These are three-dimensional arbitrarily oriented triangles. Therefore, their A, B, C, Z components may be totally different. What you should actually look at is, after you do the cross product, if the resulting, they will all be normal vectors of the plane. If one of them is, if they're all in the same direction, then it's inside. If one of them is in different direction, the opposite direction, then it will be the dot product with the normal is always 0. It will be 0. Dot product of the normal vector with this, because it's always going to be 90 degrees. Dot product will always be 0 with the normal vector. Actually, the plane equation comes from that. The plane equation, a plane is a set of points such that when we form a vector between 2 points on the plane, if you take the dot product of that with the normal vector, we get 0. And there are infinitely many points that can be orthogonal to this n. So in order to fix a plane, we need another point on the plane. So just the normal vector does not define the plane. We need some point, some anchor point like a, in order to determine to fix the plane. So with that point, any point, you form this vector p minus a, and you dot product that with the normal vector of the plane, you should get 0. Dot product. The dot product of p minus a with the normal vector is 0, and that gives actually the implicit plane equation in 3 dimensions. Oh yeah, so this one, p minus a, the normal is positive, means normal is in the upwards direction. Yeah, exactly. If the normal, so here, what I want to warn you is that the definition of positive is not well defined when you're on the 2D plane like this, okay? If this is your 2D plane and this is your x plane, this is your x-axis, y-axis, positive z will always be this way, okay? So if these triangles were on the xy plane, the definition of positive is very well defined. Actually, in that case, if they're on xy plane, the cross product will only have the z component, nothing else, all right? Which it will be a vector like this, 0, 0, z, okay? And this z will be positive if we do b minus a cross product p minus a. If p is to the left of them, z will be positive in that regard. So when I was talking about this, I first thought that they were on the xy plane. Now, just think about these triangles as arbitrary 3-dimensional triangles. They may, for example, what if this triangle itself is on the xz plane? Okay? In that case, it will be the resulting cross product will be a vector that looks like this. It will have only a y component. There will be no z component. Okay, you cannot. So these are 3-dimensional triangles. So based on their orientation, normal vectors have no meaning of opposite. But what you should be clear is that if there's an arbitrary triangle, if P is inside the triangle, the normal will be pointing to this direction towards, because we have defined the normal to be b minus a, p minus a. If we define the normal to be this, it should be pointing like these upwards from the triangle, and these may be arbitrary oriented directed vectors. There is no definition of positive here. They may all be pointing -3, -3, -3. Okay, this direction here, this normal vector here, should be -3, -3, -3. Is it negative, positive? So there is no such definition. I mean, therefore, what I'm saying is that when in 3 dimensions, when the triangles are arbitrarily oriented, all you're looking for is, are they showing the same direction? Because if a point is outside, it has to be, I mean, if a point is outside like this, it cannot have the same, these cross products cannot have the same direction, all 3 of them. If all 3 of them have the same direction, then it means that the P, I mean, if all of them are showing are parallel vectors to each other in the same direction, then P has to be inside. Yeah, the third vertex is used because I mean, these single situations is not sufficient enough. We need to look at all the 3 cross products to determine whether P is inside or outside. And as I said, so when we do this cross product, as I said, this ABC, it will result in a vector like ABC, which is going to be this normal vector. This normal vector here will have, let's call these are variables that we don't know right now. Let's call this vector normal vector ABC. We can get this normal vector by these 3 points using also the third vertex. If you cross product B minus A and C minus B like this, you will get the normal along the vector. As you can see, this, when we have a triangle, when you fix a certain direction of cross product, for example, B minus A, C minus B, what if you did C minus B cross product B minus A? It will actually be pointing in the opposite direction. So by choosing a certain orientation of like counterclockwise orientation of the vertices, we fix ourselves a front face of this triangle. We say that this normal vector is pointing from the front face of the triangle. So because given any 3-dimensional triangle, it has a front face that is facing this way, and it has a back face that is facing the other. Okay, these are just like very thin things, but they are 3-dimensional. So one of these, you have to choose yourself a certain orientation of these vertices, which will give you the normal vector that points from the front of the triangle. Now, the good thing about this ABC is that the plane equation is going to just be something like this: AX plus BY plus CZ plus D is equal to 0. And these ABCs are the XYZ components of that normal vector. Okay, so it makes it really good if you know the cross product. If you just cross product the 2 edges of a triangle, a 3-dimensional triangle, the resulting normal vector will give you 3 coefficients of A, B, and C here. Okay, how do you find D then? Just plug in the coordinates of, for example, AX, AY, and AZ here. The only unknown becomes D. All right, after you have found A, B, C, just since all these A, B, C, they are also points on the plane, plug in any one of them. You could have plugged in B. You could have plugged in BX, BY, and BZ here. Plug in one of the points in terms of these XYZ coordinates, put into this equation. The only unknown becomes D, and you solve for D, and you have your plane equation. After you have your whole plane equation, how do you find the intersection of your ray with the plane? Plug in RTX, RTY, RTZ here. You just plug in your ray equation here. When you plug in into this equation, it becomes a single equation with a single unknown T. That's how you find this point P. All right, so actually, as you can see, this involves lots of steps. First, form the plane equation with two cross products and solving this, and then plug in the ray equation to find P, and then figure out whether P is inside or outside the triangle. It involves lots of steps. There's an easier way, but more difficult to describe way to do the ray triangle intersection, and I'm going to talk about that on Thursday. Although Thursday is October 29th, we have the Turkish 97th anniversary of the foundation of our republic, but I will still have a class that morning. If you cannot attend, that's fine. You can watch the recorded video later. I mean, although it's a national holiday, I don't want to be behind. I may talk with Ozoja actually. If I don't know the schedule of the first section, if they all are also losing 2 hours this week, then we may skip that together. But if his 2 hours is on Wednesday or Friday and he's going to do that, I want to have the 2 hours of class this week as well. Okay, but since attendance is optional, you can always watch the video in any convenient time for you. All right, so that's it for today. Sorry for taking up 6 minutes of your time after the class ended. Let me know if do you have any questions? Okay, and at this point, with this method and the sphere intersection, we have finished actually the ray tracing geometry part. I will just quickly go over the alternative method for ray triangle intersection using barycentric coordinates, but you don't need to memorize the other technique. It's given in the book, but I will briefly mention that. All right, after that we will talk about how we compute the amount of color, the shading gradient of the color by using our simple shading model. Okay, see you all on Thursday. I will let you know in OctreeClass. I will make an announcement on OctreeClass about whether we are going to have a class on Thursday or not. Okay, after I talk with Ozaja. Thank you. Have a nice day. Bye bye, everyone.